thanks for showing up at 9 a.m. On Friday, we started looking at mergers that now involve neutron stars, so the sources of gravitational waves that are also going to give us powerful electromagnetic signals, black hole neutron star and neutron star mergers. And the one thing that we did have time to look at on Friday is the fact that the gravitational waves in these black hole neutron star and neutron star mergers are modified by tidal effects in the neutron stars. And so you can use gravitational waves to get some idea of the size of a neutron star and use that to get some constraints on nuclear physics in the very dense cold matter in neutron star. And we also saw that there are basically two types of black hole neutron star mergers that we can see according to numerical simulations. Let me remind you. There is one where the neutron star is ripped apart by the gravitational field of the black hole, and then you eject some matter from the system and you form a very massive disk of matter around the black hole. And there is another possibility in which the neutron star gets close to the black hole due to gravitational wave emission, and then it is just going to plunge into the black hole without disrupting what happens now. And that leaves nothing behind. So that's a lot less interesting if you want to power electromagnetic signal, because for that you need some matter left outside of the black hole. Right? And we saw that what determines which of those two outcomes actually happens is the mass ratio of the binary. If you have a very massive black hole, the second case with no disruption is more likely. The size of the neutron star, a big neutron star, is easier to rip apart. And how fast the black hole is spinning. A rapidly spinning black hole, you can get closer to the black hole before plunging, and so it is easier to disrupt as well. So high spin on the black hole is good for disruption, low mass on the black hole is good, and a big neutron star is also good. Right. So that was what we did on Friday. And let me say a few more words about what happens during and after merger, and then we'll move to neutron star systems, and all of the post-merger evolution after that. So one thing to note on the movies that I just showed you is that if you have one of those disrupting neutron stars, you are going to eject a significant amount of matter into the surrounding interstellar medium. Typically, if the neutron star disrupts a few percent of a solar mass to maybe up to 10% of a solar mass, so a very large amount of matter, of very neutron-rich matter, about 95% neutrons, which is going to be unbound and sent into the surrounding interstellar medium. And that ejecta is pretty fast, between 10 to 30% of the speed of light. So there's a lot of kinetic energy there, and that's one way in which we can observe it, maybe is through the radio emission as it decelerates into the interstellar medium. That's not the one that we have seen so far. What we have seen so far, as we will see later, is the radioactive decay into that material. And we have predictions for what amount of matter is going to be ejected for any given black hole neutron star merger. And generally speaking, again, if you have a big neutron star, it's going to be ripped apart farther away from the black hole, and it's going to be also easier to rip it apart, and you're going to eject more material. Relatively speaking, if you have a higher mass ratio, so a more massive black hole, and the neutron star disrupts, you are going to have more mass that is unbound compared to the mass that remains in the disk. So you leave more mass outside of the black hole if you have a low mass black hole, but relatively speaking, more of that is going to be ejected into the surrounding medium if it's a higher mass ratio. So depending on the properties of the system, you are going to have very different ejecta, and that's really the important thing, is that using the amount of mass that is ejected in those systems, we might be able to get an idea of what the emerging objects actually were. We might get some information about the size of neutron stars, about the mass and spin of the black hole.
Large neutron star in a large radius or large mass?
Large radius. Large radius, yes. Large radius is better. Large mass is worse, because usually large mass means more compact, and so harder to disrupt, yes. Thank you. So bigger neutron star, wider. Thank you. Usually smaller mass, neutron stars have nearly the same radius as all mass, so smaller mass means less compact and easier to disrupt, yes, usually. If we understand the equation of state as we think we do. And okay, one thing to note about the dynamical ejecta from black hole neutron star merger is also that it is very confined to the equatorial, to the orbital plane of the initial binary. So this gives you the distribution of ejecta in a few black hole neutron star merger. The vertical axis is the angle with respect to the orbital plane, and the horizontal axis is the azimuthal angle. And you see that it's confined within about 20 degrees of the initial orbital plane, so it remains very, very close to this. Yeah, this is work done by Drev when he was in Berkeley. So that's one thing that we will be able to use to get electromagnetic signals from these neutron star mergers, is that matter which is ejected at the time of merger. The other thing that we are left with after the merger is that hot massive accretion disk around the black hole. So we have a black hole which is still very close to the initial mass of the pre-merger black hole, because typically the black hole is much more massive than the neutron star. And then you have maybe 10% of a solar mass, order of magnitude. It can change easily by a factor of a few in the surrounding disk. And that disk is very hot, a few MeVs, and fairly compact as well. Everything, the entire disk at first is within maybe 50 to 100 kilometers of the black hole. So very, very compact system. And that's what is going to be present after the merger, when what we have at our disposal to try to produce post-merger electromagnetic signals. And we also know how much matter is in that disk for any given neutron star and black hole system. And so again, this is going to depend on the parameter of the binary, so the mass of the black holes, the size of the neutron stars, and so on. So if we can relate electromagnetic signals to how much matter was present after the merger, which is a hard thing to do, we might also get some ideas of what the parameters of the merging objects were. So that's during the merger of a black hole with a neutron star. We can have a quick look at what happens when we instead have two neutron stars. And the movie that I'm going to show you, it's only showing the bottom half of the merger so that we can see the center of the neutron stars. And so you're going to see what happens when the two neutron stars merge in this case. These are very low mass neutron stars. So again, they are going to collide. At the time of collisions, you can have some matter ejected, both from the shock between the two neutron stars and from tidal disruption. And then you end up with a ringing massive neutron star remnant surrounding by what's starting to form an accretion disk in this system.
So you're simulating up until the center of the neutron star, like there's no boundary condition at all.
In this? Yeah, so it's not like the black hole. In the black hole case, we remove well, at least in those simulations, we remove the center. You also can do that puncture method, which you have a singularity moving on your grid. But in the neutron star case, yeah, we evolve the entire space-time there. There is no excision because there is no singularity, so we don't have any problem with the center of the neutron star.
But if there were a singularity from the merger, that would be
yeah.
handle that.
So yeah, it's a little more complicated. But what can happen is you might have more massive neutron stars here, and then they collapse to a black hole. And you monitor whether you are forming a horizon in your simulation. And if you do form a horizon, then you can remove that from your simulation, put an excision region there, put a boundary there, and then treat it as the black holes before. But it's a bit more complicated because you have to monitor whether you form a black hole, and then you have to remove the black hole from your simulation, probably use a new computational grid that is more adapted to that kind of. So there is a lot of extra steps there. If you want to have a black hole. But technically, I mean, in theory at least, it's not much harder than evolving two black holes. It's just actually figuring out what the black hole is a little bit complicated sometimes. Any other question? Yeah.
And this matter in the outer parts of this new compact object, it's also neutron gas, very dense neutron gas.
So it is still largely neutrons. In the outside of the neutron star, once you take into account neutrino matter interactions, which we will discuss a little bit in a minute, it's roughly 75% neutrons, 80% neutrons, something like that at first. And then and it's still very dense. It's 10 to the 11 gram per centimeter cube in the inner disk. So it is still very dense and very neutron rich. And actually, over the evolution of the disk, if anything, it becomes the core of the disk becomes even more neutron rich.
But how is pressure sustained? Because in the neutron star we have this pressure which is made by gravity, and in that case you have some high rotation case, and the gravity is equalized by the.
Yes. So the density is much lower than in the initial neutron star, and as this spread out, the density decreases, and you get more towards something closer to normal matter. But it takes a long time before you actually get to a place where the matter looks more like what we.
I thought in the supernova case, when you lost this pressure, you usually get some fusion reactions and produce a lot of metals and so on.
Right. So on a time scale of about a second, you are going to start recombining into alpha particle, for example. That happens, and that is important for the long post-merger evolution. But it takes a bit long. It's not on the time scales of the merger. It takes longer, and you have to go well below the densities that you have right around the neutron stars. But as the disk spreads and the densities decrease, then you are going indeed to recombine into alpha particles. And for the ejecta, you are going to get a lot of other reactions that we will see that come into play. Yeah. Let's answer your question. Any other question on this? Okay. So, like for black hole neutron stars, for neutron star mergers, we are going to eject matter into the surrounding medium. We know there are multiple ways to do this because the system is a little bit more complicated with neutron stars. You still have the same kind of tides and tidal tails that are formed during the disruption of a neutron star by a black hole. Here it's most, you have one from each neutron star generally. And that matter is still going to be very cold and very neutron rich. But you can also get matter which is ejected during the collisions between the two neutron stars by squeezing and heating the matter which is in between the two neutron stars. And that one is typically a little faster, it's hotter, and we see that because it is hotter, it can actually change its composition and becomes less neutron rich and has more protons. It's still neutron rich, it's probably still between 60 and 80% neutrons, but not as much as the initial neutron stars, and that's going to be important for electromagnetic signals. And again, you can get an idea of how much matter is ejected by any given neutron star merger. Typically, the cold dynamical ejecta from the tail is again produced in larger quantities if you have a large radius for the neutron star, and if you have asymmetric masses. So if the two masses are equal, there is nearly no tidal tails formed into the system. And the squeeze ejecta, on the other hand, it's stronger if you have a strong collisions between the two neutron stars, and that's better if the neutron stars are small. If the neutron stars are small, they are going to hit each other faster. So that's how you get more of that squeeze hot ejecta. I say, but not too small, because generally if they are too small, they are also neutron stars that are going to collapse into a black hole because they tend to be more massive, or have equation of state which supports lower black hole masses. So, and then you don't have anything that is ejected from the merger. So it's not a monotonous function of the size of the star. Yeah. And an important difference with the black hole neutron star system is that now your ejecta is going to go all over the place and not just in the equatorial plane. This is shown in these simulations by Kentaro Takezaka. Which you can see on the left, an equatorial slice in the orbital plane of the binary. On the right is a vertical slice. And you see that there is ejecta which is sent in all directions. The tidal tail ejecta is still mostly in the equatorial plane, but now there is a lot of that ejecta coming from the collision between two neutron stars, which is sent all over the place. So you have a much more uniform distribution of matter that is ejected. All right. So what is the result of these mergers? We've already seen a good part of that in Sylvia's talk. there are basically three possible outcomes to a neutron star merger. Either you have low mass stars, and when they merge, they form a neutron star which can still be supported, by nuclear forces, which does not collapse to a black hole. It is below the maximum allowed mass, and then you are going to form a neutron star surrounded by an accretion disk. And because rotational support can help you keep the neutron star, can help the neutron star survives, you can actually keep that setup up until maybe 20% above the maximum mass allowed for a neutron star. So if the maximum mass for a neutron star is 2 solar mass, which is the minimum value that it could be, because we have observed a 2 solar mass neutron star, then maybe that is true if the 2 neutron stars are up to 2.4 solar mass or so. It depends a little bit on the equations of state, but roughly speaking, that's what it is. The other extreme outcome is that the 2 neutron stars are so massive that as soon as they collide, they collapse to a black hole. They cannot support themselves at all against gravitational collapse. And that's true typically if you are above, roughly 40% above the maximum mass of a neutron star. So maybe for maximum mass of a neutron star, 2 solar mass, 2.8 solar mass or so. But if the maximum mass of a neutron star is much higher, then you need maybe 3 or more solar mass of matter in order to collapse immediately, which is probably not the case for most neutron star mergers. And then the in-between case, you are going to form a massive neutron star, but it's too massive to support itself against gravitational collapse once it has redistributed its angular momentum. Initially, the star is differentially rotating, but it's going to become more uniformly rotating over time. And then when that angular momentum has been redistributed, the neutron star collapses. And that is what happens, in between, but roughly 20 and 40% above the maximum mass for a neutron star. And given what we know about the equation of state of neutron stars and about the masses of neutron stars in galactic binaries, this one and maybe the one with the stable neutron stars are the most likely cases. But if you had very massive neutron stars in binary systems, the direct collapse to a black hole would also be possible.
During the formation of the black hole, how does the black hole form? Because it first forms an arbitrarily small black hole and then rapidly with surroundings. There's a big chunk of matter in the black hole.
So the event horizon, I guess, would start from in some slashing at least would start from a point, and then you would start to grow it. In your simulation, you don't notice it when it's just a point. It's when the horizon has grown a little sufficiently, then you can actually observe it in your simulation. So, but physically, yeah, it should grow from at some point there is a region from which no information can reach spatial infinity, and that's where your horizon starts. But that can be hard to find in simulations because you don't know how the system is going to evolve in the future, and so you don't know how light rays, for example, are going to evolve. So there are two questions. There is the horizon as you would reconstruct it after knowing the full 4-dimensional evolution, and then there is what you can actually figure out in the simulations at a given time. Those are two different questions.
So some people say that the neutrons in the neutron star have this property of fluidity, so they have generally no viscosity. And if you merge two neutron stars, can you possibly produce some kind of neutron disk which will be stable on the long time scales?
So there is no viscous, but there are effective viscous effects like come from magnetic fields and from maybe a little bit from neutrino transport as well, but mostly from magnetic fields that are going to redistribute angular momentum. And so the neutrons are still, there is still some effective viscosity that comes into the system. Okay. All right. And so in terms of gravitational waves from these systems, so we have already seen that before merger you can get some information about the size of the neutron star from tides in the neutron star. And in black hole neutron star system, you can get some information about the size of the neutron star from the cutoff in the gravitational wave signal which comes when the neutron star is destroyed. All right, so suddenly the gravitational wave signal stops at a given frequency when the neutron star is destroyed. In neutron star systems, things are a little bit different. You still get the tides in the inspiral, but you don't get destruction of the neutron star. Instead, what you get is a big neutron star which is very strongly distorted and is going to ring mostly at its fundamental excitation mode and emit gravitational waves at the frequency of that mode. And you can see that here. So these are spectrogram of the gravitational wave signal. So time on the horizontal axis and frequency on the vertical of the gravitational wave on the vertical axis. The tail end at the bottom left of each plot is the merger signal, so the rising chirp that we have seen in many different systems already. And then you see that after merger, most of the power is around one frequency. And that frequency depends on the properties of the neutron star. So here I'm plotting 3 different equations of state, or 3 different neutron star radii if you prefer. And you see that the frequency of the gravitational wave signal is different in each of them. And you can actually predict reasonably well what that gravitational wave frequency should be for any given equation of state. So if you were able to measure that, it would be a fairly clean measurement of the properties of neutron star at high density. Unfortunately, if you look at the actual frequencies, it is 2 to 3 kilohertz here, and these are still pretty big neutron star, 12 to 13 kilometer. If you go to lower radii, the frequency rises even more, and so it's pretty much out of reach of the current LIGO detector, and still very, very difficult even if you increase the accuracy of LIGO at high frequency. So this is a very difficult measurement to make. In some way, it is a cleaner measurement of the properties of neutron stars than what you can get in the pre-merger signal, because you just measure one frequency and you can immediately relate it to a fundamental property of the neutron star. But it's a very difficult measurement to make for LIGO, unfortunately. And again, as a result of that merger, so you are going to be left with either a black hole or a neutron star now, surrounded by an accretion disk, fairly similar to the black hole neutron star case, maybe a little bit less mass in the accretion disk, and then some matter, both bound and unbound, which is in the tidal tail. The amount of unbound material in the neutron star merger is typically smaller than in black hole neutron star merger, maybe up to 1 or 2% of a solar mass at the time of the merger only, compared to a few percent to 10% of a solar mass for black hole neutron star. So you eject less matter in the neutron star merger, which might be important for electromagnetic signals. And the properties of the disk are fairly similar to black hole neutron star mergers otherwise. All right, and then after the merger, so you have formed that black hole or neutron star plus an accretion disk, and then there is a lot of extra physics that comes in, and we will look a little bit at that later. But to summarize, what happens is you're going to get a lot more outflows from that accretion disk plus black hole or neutron star, some driven by magnetic fields, some driven by neutrinos, and some from the viscous spreading of the disk, which is actually also magnetic fields. It's due to the growth of the magnetorotational instability in that disk, which you have already heard about in filametage talk last week, and I might come back to it later on. But basically, the disk is going to spread out, transferring angular momentum thanks to that instability. And over time, it's going to spread and unbind a significant amount of its mass. And you can see here that this is the mass ejection as a function of time. The black curve is the one that matters. So over a time scale of about 1 second, you have a lot of magnetically driven outflows. And then you have viscous outflows from 1 second to maybe 10 seconds or so, and then it shuts down after that. And during that phase, during those 1 to 10 seconds of evolution there, you are going to unbind a significant part of the disk, depending on the simulation, somewhere between 20 to 40% of the mass of the disk. So if you remember that the disk was typically maybe 10% of a solar mass, so again, that's a few percent of a solar mass on top of what we had during merger. So in the black hole neutron star merger, this is probably a somewhat subdominant contribution. It's a little less than what was in the dynamical ejector. But in the neutron star merger, this may be the most important contribution to the amount of mass that you eject. this may be where you eject most of the mass, because typically the merger doesn't eject that much, maybe up to percent, while this can eject a few percent of the solar mass. So this is probably where most of your matter is going to be ejected. And roughly speaking, it's about half and half between the early magnetically driven outflows and the later times viscously driven outflows. All right. So now we are going to slowly move towards the electromagnetic counterparts that come from these black hole neutron star and neutron star mergers, and especially the kilonova, the optical infrared signal that is powered by the ejector. But before getting into that, one important thing for the properties of these electromagnetic signal will be, and we'll see why, the composition of the outflows. So the relative number of neutrons and protons in those outflows. And to understand how that changes depending on the type of outflows, we have to look at neutrino physics in these mergers. So that's when all of the extra physics beyond just hydrodynamics and general relativity comes into play. It's during those post-merger evolutions. And one of those aspects is neutrino physics. The other important one is magnetic fields. So if you have a neutrino, if you have an accretion disk around a black hole or a neutron star, and it's typically at densities of, as we mentioned, 10 to the 11, maybe gram per centimeter cube. That disk is entirely optically thick to photons. Photons cannot escape the disk. The only way the disk can cool is by emitting neutrinos. And even neutrinos, which usually you think as not interacting much with anything, even neutrinos have optical depths of a few in the accretion disk. So even neutrinos are going to have a few interactions before escaping that accretion disk. And the neutron star itself is optically thick to both neutrinos and photons. And so neutrinos are going to play a number of important roles. One of them is to cool the remnant accretion disk. And we'll see a few of the others on the next slide. The way in which neutrinos come into play for cooling and for changing the composition of the system is through a set of reactions here. The first, and maybe the most important, is charged current reactions in which a proton can capture, for example, an electron and give you a neutron and electron neutrinos, or the inverse reaction in which an electron neutrinos is captured by a neutron and then gives you a proton and an electron. So that's one way in which you can change protons into neutrons and vice versa by emitting or absorbing neutrinos. And you have also the reaction with positrons in which a neutron captures a positron and produce a proton and an electron antineutrino, and the inverse reaction. So all of those reactions, which are generally the dominant reaction for electron-type neutrinos, are going to change the composition of the matter, which we parameterize by that electron fraction YE, which you will often see in discussion of neutron star mergers, which is the number density of protons or equivalently electrons, because the matter is charge neutral, divided by the total number of protons and neutrons. So that's usually the parameterization that we will use. But so a low YE is very neutron rich, and a high YE is very proton rich. And standard matter is around 0.5, but neutron star YE of 0.5. But neutron stars initially are more around YE of 0.05, 5%. Okay. And then there are other sets of reactions, such as, for example, electron-positron annihilation into neutrino-antineutrino, or vice versa, neutrino-antineutrino annihilation into electron-positrons or into phonons. And then there is also a Bremsstrahlung in which two nuclei interact and emit a neutrino and an antineutrino pair. Those happen for both electron neutrinos and for all of the other type of neutrinos, muon and tau neutrinos and antineutrinos. And they are subdominant for the electron type, but they are the main reactions for the other types of neutrinos. And all of these reactions are very strongly dependent on the temperature of the matter, T to the temperature to the 4 to temperature to the 8 or 9 in some cases, depending on the reaction. And so if you have a hot ejector, it is going to emit and absorb a lot more neutrinos than if you have cold matter. And The last thing that could happen is oscillations of neutrinos between electron neutrinos and muon and tau neutrinos. And that is something that in current simulations we're not capable of including that directly in the simulations. But there have been studies looking at what the profile of a post-merger system looks like, that have looked at how much neutrino oscillations you would expect, and in some cases you can actually have some non-negligible transfer from electron neutrinos to other types of neutrinos. So this could possibly play a role, probably not in the cooling of the system, but maybe in the evolution of the composition. If neutrino oscillate if neutrino oscillates out of electron neutrinos into muon or tau before they can interact with the ejecta and change its composition. So that could be important. So schematically speaking, here's what we have. We have an accretion disk, hot accretion disk, which is heated by magnetically driven turbulence, as we will see, but is cooled by neutrino emission. And then neutrinos, as they propagate, might be absorbed in the low density regions above the disk. That's how you can generate a neutrino-driven wind, is by absorbing a lot of neutrinos in the lower density regions on the outskirts of the disk. So that's one way in which you can eject material after the merger. It is probably not the dominant mechanism. Magnetic fields are more efficient at that, but it's one way in which you can do it. And then you have all that matter which is moving away from the remnant, all of the unbound material. And there you can absorb neutrinos and possibly re-emit neutrinos that are emitted from the central object. And in terms of neutrino-matter interactions, one very important question is whether at the center you have a black hole or a very hot neutron star. That is going to significantly change neutrino effects. The reason for that is that if you have a very, very hot neutron star in the post-merger remnant, it is going to be a very strong source of neutrinos. And so you will have a lot more neutrinos available for absorption into your ejecta, and you might change the composition of the ejecta much faster if you have a neutron star at the center rather than a black hole. So that's an important distinction, and that's also one way in which we might be able to tell whether a neutron star survive for a long time or not in that system. Again, if we can make measurements of the properties of the ejecta well enough. Okay, so we mostly covered that. Strong temperature dependence of the neutrino-matter interactions, and we can drive wind with neutrinos, and we can change the composition of the matter with neutrinos. The last thing that neutrinos might be useful for is if you have neutrino and antineutrino annihilating above the remnant disk. In the polar regions where there's above the disk, you can have neutrino and antineutrino annihilating, depositing energy there, and that can have a number of effects. It can drive matter away from that region, creating a matter-free region there, which might help later on to produce a jet, or it could itself drive relativistic outflows. That was one of the mechanisms which originally was proposed for gamma ray burst. But from current simulations, it seems that there is not quite enough energy in the neutrino emissions to do that just using neutrinos. The neutrinos might help with the production of a gamma ray burst. They probably do not produce the gamma ray burst themselves, but that's not entirely settled yet. And here is where the energy is deposited due to neutrino and antineutrino energy per unit mass. You can see that most of the energy deposition is in those polar regions. This is a vertical slice through a neutron star merger remnant. Most of the energy deposition is in that polar regions there where you have lower density matter being flown out, and where actually most of your neutrinos are being ejected if you have a neutron star at the center. On the left, you can see the effect of the change of the neutrino absorption and emission on the composition. This shows you the electron fraction. You can see the neutron star at the center, again, is 5 to 10% protons only. The rest is neutrons. The surrounding accretion disk, as we discussed earlier, is maybe 15, 20% neutrons. But then you have those regions at the poles where the matter is a lot hotter and you have a lot more neutrino absorption and emission. And you see that there you can drive the electron fraction to nearly 50%, and actually on average maybe about a bit above 30% neutrons. So there you have significant change in the number of neutrons and protons in the ejected material. And you only capture that if you properly do the neutrino-matter interactions in simulations. So that's very costly to do in simulations. So many of the simulations of neutron star mergers that we have so far do not have sufficiently accurate neutrino-matter interactions to actually tell you what the composition of these outflows are. And that's one limitation of our current models of outflows. Many simulations are capable of getting an idea of how much matter is ejected, but not how it interacts with neutrinos and what its composition is. And we might later on have a look at what is needed to actually evolve neutrinos in simulations, if time permits. All right, so once you take into account neutrinos, you can get a rough picture of what kind of outflows you have in neutron star, and black hole neutron star mergers, and what their properties are. In black hole neutron star mergers, probably the strongest outflow component on the right is that tidal dynamical ejecta, so what comes from the disruption of the neutron star. And that's very neutron rich and relatively large speeds, 20 to 30% of the speed of light. And then you have that other component which comes from either neutrino-driven or magnetically driven, or the outflows, or the long-term evolution of the disk, which is going to add a few percent of solar mass of disk winds outflows, which is generally much lower velocity. And depending on the properties of the binary, you might get more of one or more of the other. So typically, equal mass system gives you more of the disk winds type of outflows, and unequal mass system will give you more of the tidal ejecta. In neutron stars, you have the same two components, but on top of that, you have that shock component coming from the collision between the two neutron stars, which is hotter, and so is going to have less neutrons and more protons. And it's typically fairly fast as well, 20 to 30% of the speed of light, with maybe even some components that goes to 70, 80% of the speed of light. Also, that's more controversial because there is very little mass in there, and it's hard to capture in the simulations. And in neutron star mergers, the disk wind can be very different depending on whether you have a neutron star at the center or a black hole at the center. Because if you have a neutron star at the center, you can absorb and emit a lot more neutrinos. And so you are going to have a lot less neutrons in the disk outflows if you have a neutron star. All right. So that's the global picture of the type of outflows that we generate in these neutron star, and black hole neutron star systems. So now we're going to see why it actually matters for observations. How much mass is ejected into each of those components, and what the composition of the outflows is. And when we understand what impact it has on observations, then we can try to figure out, can we actually go back and extract information about the parameter of the merging objects from observations of these outflows? Because each type of ejecta comes in different quantities depending on the properties of the merging objects. So, any question on the outflows first, maybe? No? All right. So let's look at this picture that has been shown a lot in talks about what kind of electromagnetic counterparts you can have in these black hole neutron star mergers. And I'm going to focus mostly on the kilonova, but you will hear a lot more about the others from Samaya over the course of this week. So what you expect in a black hole neutron star merger is that at least some of these systems are going to drive a powerful relativistic jet from the black hole disk remnant, like you have seen in some talks last week. And that will be visible, hopefully, as a gamma ray burst. And we think that that's what we have seen in the neutron star merger that we have observed already is one of those gamma ray bursts, also slightly off axis. And that gamma ray burst is going to be followed by afterglow pretty much in all frequency bands. There's another important emission which comes from the kilonova, from the ejecta, and that's going to be optical or infrared emission on a time scale of a few days to a few weeks. And we'll see exactly what happens later on. And then as it expands into the interstellar medium, that ejecta will interact with the interstellar medium and emit in the radio. So how does that kilonova emission come about? Well, you have a merger. It ejects a few percent, let's say, of a solar mass of neutron-rich material into the surrounding medium. Now, as that material expands and cools, it is going to, you are going to have some seed nuclei which are going to rapidly capture neutrons. You have a lot of neutrons available, and they are going to rapidly capture neutrons and form very neutron-rich, heavy nuclei. And then at some point, when you don't have that much neutrons left into your ejector, you run out of neutrons, and those very neutron-rich nuclei are highly unstable. They are going to rapidly decay back towards stable heavy elements with only a little bit more neutrons than protons. And that's the way in which you form a lot of the heavy elements in the universe. At least that's one way to form them. What are called the R process elements, rapid neutron capture nucleosynthesis elements. And we will see the exact nuclear processes that come into that on the next slide. But you are going to form those very neutron-rich massive elements, and then as during the radioactive decay towards more stable elements, they are going to release energy into that ejector. And at first, the ejector is dense, and it is optically thick to photons, and so most of that energy, the part that doesn't go into neutrinos, is just deposited into the ejector. But at some point, because the material expands and the opacity decreases, it is going to actually start releasing that energy as observable photons, and then you get something that is either an optical or infrared emission, depending on the opacities. So that's because that's of the time at which that energy is released. The temperature is such that most of the emission is in the optical or infrared. And so you might get an emission from those radioactive decay on a time scale of a few days to a few weeks after the merger. Okay? And of course, this is going to be very sensitive to what the opacity of your ejector is, because that determines what the frequency of your emission is at the time at which the energy is released, and also the time scale on which it is released. So that's very important if you want to actually observe this, is knowing what frequency should you look at to observe this, and when should you look at it after the merger. All right, so let's look a little bit more at the nuclear physics of this. So this is a relatively busy plot, but it's a movie you're going to see. And what you are going to see is the distribution of nuclei. The vertical axis shows you the number of protons in a given nuclei, and the horizontal axis is the number of neutrons. And the solid squares on that curved line in the middle are the stable nuclei. Right? And the first movie that I'm going to show you is for very neutron-rich material ejected from, for example, a black hole neutron star merger. So this is material that starts with, in this case, about 10% protons and 90% neutrons. And you start from the bottom left here. Most of your matter is in the bottom left here, with a few heavy nuclei and mostly neutrons. Now, as the matter expands, you capture a lot of neutrons, and you are going to start forming those very neutron-rich nuclei. So you see you are very far away from the region of stable nuclei, and you form that series of very neutron-rich nuclei by continuously capturing neutrons and then occasionally decaying back towards a more proton-rich nuclei, but you have so many neutrons that you keep capturing neutrons, and you form those more and more massive nuclei. And most of the nuclei actually end up being in those solid vertical lines, which are slightly more stable neutron-rich nuclei at nuclear magic numbers here. So, sorry. There we go. So let's restart this. So you form that series of very neutron-rich nuclei. Once you get to very, very massive nuclei, then they fusion back into about half the mass. And at some point, you run out of neutrons, and everything decays back towards stability. That can take a long time. And this is the point at which your kilonova signal comes in. It's due to the energy released during that stage here. What you can see is that there are regions, the red regions here, where most of your nuclei and where most of your matter ends up. So it's nuclei that are around, let's see, neutron number of 76 and 120 maybe. And that is the characteristics of nuclei which have been formed in that neutron-rich environment, because they are the decay product of the slightly more stable nuclei that were at neutron magic number there. If you had formed those nuclei by slower neutron capture following the curve of stable nuclei, which is another process to form heavy nuclei, which is called the slow neutron capture process, or S process, you would have most of your nuclei at the magic number that on the curve of stable elements, so slightly higher masses for each concentration of heavy nuclei. So you would have a different distribution of nuclei if you had formed them into a less neutron-rich environment. And you see that here you end up forming nuclei mostly at relatively high mass on the right part of this plot. The other type of ejecta that you can produce in these black hole neutron star mergers, as we have seen, is something with less neutrons. Here it's still fairly neutron-rich matter. It's still 75% neutrons and 25% protons. So we'll see that what happens is slightly different when you get above roughly 25% protons. No, you are still going to do rapid neutron capture. Actually, yes, okay. But now you are going to run out of neutrons before you can form the heaviest elements, and then you decay from there. So you're still going to form a lot of heavy elements, but not as high in the periodic table as you would if you had more neutrons. Your rapid neutron capture process is cut a bit short, and so you form those less massive elements here if you have less neutrons available. And they still have those characteristic peaks of amplitude at the decay products of the slightly more stable elements along the path of the R process, but now at lower mass than in the previous movie. So that's one important distinction between those neutron-rich and less neutron-rich outflows, is that the very neutron-rich outflows are going to produce very heavy elements. The less neutron-rich outflows are going to produce less massive elements. And this is particularly important if you try to explain the production of those heavy R process elements using neutron star mergers. Because if we look at the distribution of R process elements, for example, in the solar system, you see both components. You see the low mass ones and the high mass ones. And so if you want most of your R process elements to come from neutron star mergers, your merger better produce both types of outflows. The ones that produce the low mass elements and the one that produce the high mass elements. And they have to be produced in the right ratio so that we can reproduce the actual observations of our process elements. And so you do need both neutron-rich and somewhat less neutron-rich outflows if you believe that neutron star mergers are the main source of our process elements, which seems to become more and more likely now that we have actually observed a neutron star merger ejecting a significant amount of matter into the surrounding medium. So that's one important consequence of that difference between the neutron-rich and less neutron-rich outflows, is that they give you different element production. Right? The other important distinction is that those heavy elements, the ones that are produced in very neutron-rich environment, have very high opacities, especially at least in the optical infrared frequencies that we are interested in here. And that means that if you produce those very heavy elements, you are going to take longer to release the energy that is deposited by radioactive decay in those outflows. It is going, if you produce the lower mass elements, the opacity is lower, and so you can release the energy earlier and generally at higher frequency, at shorter wavelength. If you form the massive elements, you have higher opacity, it takes you longer to release the energy, it is released at lower frequencies. So that's going to significantly affect the electromagnetic properties of your mergers here, because you are going to end up with something that is either, if you form very heavy elements, going to be to have its energy released in the infrared on a time scale of maybe a week or two after the merger, or if you form only the lighter elements, you are going to have an energy which is released in the optical, mostly on a time scale of a few days after the merger. So the kilonova, the optical emission coming from these outflows, is going to be very different depending on whether you have neutron-rich or not neutron-rich outflows. So we can actually look at a little bit more detail at how the different properties of the outflow affect the kilonova light curve, so the emission from those radioactive decay. And the main things that affect the kilonova are the opacity of the outflows, so the composition, the total mass of the outflows, and then also the expansion velocity, how fast they are moving away from the remnant, and the geometry of the outflows, which is going to affect, well, especially how the kilonova looks, how the change in the kilonova appears as you change the orientation of the system with respect to us. So here are a few bolometric light curves for kilonovae that were produced by Jennifer Barnes and Dan Kaysen, which show you some of that dependence. So the black line is the type of kilonova that you would get if you eject about 1% of a solar mass, and you assume that the opacities are similar to iron, which is also typical of what you get for very neutron-poor ejecta, or less neutron-rich ejecta. On the other hand, if you do have those higher opacity heavy elements that are formed in neutron-rich ejecta, for the same amount of mass, you go to the blue curve, right? So the emission comes over a much longer time scale. The amplitude of the emission is generally lower. And what is not shown here, but that can also be computed using those models, is that it goes from being optical emission to being mostly infrared emission. And you can also see the change in the mass. That is easier to understand. If you have less mass, you have less luminosity in those outflows. So 10 to the minus 3 solar mass is the purple curve, 10 to the minus 2 the blue curve, and the green curve is 10 to the minus 1 solar mass. And so the more mass you eject, the higher the amplitude of your signal, and the longer the duration of your signal as well. And the velocity also has an important effect on how long it takes, because that's what is going to determine the expansion rate of your ejecta, and so when it actually becomes optically thin to photons. And again, if you have a low expansion velocity, so 10% of the speed of light is the blue curve here, it takes a fair amount of time for it to expand and become optically thin. But if you have a high velocity ejecta, maybe 30% of the speed of light, like the purple curve, then it expands a lot faster, and the energy is released earlier. The expansion velocity is also going to affect things like the width of any lines that you might have in your spectrum, which is another way in which you can determine what the velocity of the ejecta was. Okay, so that's roughly what you can use to actually extract information from those kilonova signals. So you're going to observe a kilonova like in the neutron star mergers, and Samaya is going to talk a lot about that. And then you see a certain amount of energy coming at early times in optical bands, a certain amount of energy coming at later times in infrared. And from that you can try to reconstruct how much matter was in neutron-rich ejecta and how much matter was in less neutron-rich ejecta, and maybe what the velocities of these different components were. And that's something that has been done with LIGO, and that I'm sure Samaya will show you later in this series. And then if you have the amount of mass in each component, well, you can figure out how much of each type of heavy element was deposited, and so do those neutron star mergers actually significantly contribute to the production of those R process elements, things like gold, uranium, platinum. And once we have more neutron star mergers, we will be able to tell from those observations, whether neutron star mergers are actually responsible for most of the R process production in the universe or not. At the moment, it seems likely, but with one event, you can't really know what the actual event rate is, and so we will have to wait a little bit more to know what the actual production rate of these heavy elements in neutron star merger is. And the other thing that you can do is try to infer information about the parameters of the binary, the masses and the size of the neutron star, for example, and use that in conjunction with gravitational wave observations to get better constraints on the parameters of emerging objects and maybe on the equation of state of neutron star. But that's harder because you need reliable models for those outflows, and that requires much more accurate simulations than what we currently have at our disposal. Any question on that before I move to more microphysics? Nope. Okay. So for the last maybe 15 minutes or so, I'm going to try to give you an idea of why those simulations of post-merger evolutions of post-merger neutron star and black neutron star evolutions are difficult. What is currently limiting our ability to make these models of outflows. And this comes in part from the neutrino physics and in part from the magnetic fields evolution in the post-merger. So let's look quickly at what the impact of magnetic fields is on the evolution of these neutron star mergers. So you expect the neutron star to be somewhat magnetized. So this relatively busy plot shows you the observed pulsars and magnetars as a function of the period of the neutron star and the time derivative of its period. And from that, making some assumptions about the geometry of the magnetic field, you can get an estimate of the strength of the field, which are those green lines coming across the solid green lines. And we observe neutron stars with inferred magnetic fields of, well, in this plot up to 10 to the 15 roughly. For the stronger magnetars, you might get a little bit higher than that. But most of the neutron stars observed as pulsars are maybe at 10 to the 12 Gauss. And then there are even lower magnetic fields in neutron stars that we don't even observe as pulsars, which are likely to exist. So let's say most neutron stars, if we are not observing magnetars, we maybe be at 10 to the 12 Gauss or lower for the magnetic field. And there have been studies of what happens before merger if you put certain magnetic field inside of a neutron star. And you might get some electromagnetic emission from interaction between the magnetosphere of neutron stars, although it is relatively weak compared to the other signals that we have been talking about. But in terms of the dynamics of the system, in terms of the gravitational waves, if you really want to have an effect on the evolution of the system, you need to put inside a neutron star a field of the order of 10 to the 17 Gauss, so, roughly speaking. So from that, and the fact that we don't expect neutron stars with 10 to the 17 Gauss in those most neutron star mergers, at least, we infer that before the objects merge, the effect of magnetic field on the dynamics of the system is probably not very important. Where it really becomes important is in the post-merger evolution, and that's because the magnetic field is going to grow due to a series of instabilities. The first one, which is mostly occurring in neutron star merger, is the Kelvin-Helmholtz instability, which is stability occurring if you have a shear region between fluid regions moving in different directions, and you form those very turbulent motion then eddies at the interface between the two neutron stars, and that instability is going to grow fastest on on the smaller scale that do not dissipate immediately. So you are going to have very fast growth of very small scale instability and forming those very turbulent flows. And that occurs, for example, in the contact region between the two neutron stars, because you have one neutron star moving in one direction, the other moving in the other direction, and when they get into contact, there is a very strong shear at the interface between the two stars. And one effect of this instability is to very strongly grow the magnetic field inside the star. So this is probably the best simulation of that effect in neutron star merger so far by Kenta Kiyoshi and the Kyoto group. At the top, you can see the density and velocities in the fluid of the two neutron stars as they merge. And at the bottom part, you can see the growth of the magnetic field strength. And you can see that in the shear region, and actually also at in the surface of the neutron star, you grow a magnetic field up to 10 to the 15 to 10 to the 16 Gauss in these systems. What you cannot really see clearly on this plot, but it's not clear in the simulation, is that the more resolution you add, the smallest your grid size is in these simulations, the more small-scale structure you see, and the fastest your magnetic field grows. And so far, as we keep increasing the resolution, we keep getting different results. The magnetic field grows faster and faster, and you get smaller and smaller scale features, and the simulation results are not converged. So that's one very difficult part here, is that we would like to know what the magnetic field is after merger, because that's very important for the post-merger evolution of the disk and for the evolution of the remnant neutron star. But the simulations that we can afford do not have enough resolution to capture this instability and do not seem to converge to a well-defined answer. So that's a significant issue. We know that the magnetic field is going to grow to very large values, but it's in a very turbulent state here, and we don't know what the large-scale structure of the magnetic field is going to be, and we cannot currently predict it with simulations. So all of the studies that have been done of the effect of magnetic field after the merger tend to make up a magnetic field in the post-merger remnant and see what happens. You put a large-scale structure magnetic field, assuming that somehow all of those turbulent magnetic field gives you something that might have some large-scale structure. But really, we can't prove that. It's just something that we put in the simulations by hand in order for the simulations to be manageable. So that's an important open question here is, how do you go from those small-scale fields to whatever large-scale structure you might have after the merger. The other important magnetic effect in this post-merger evolution is the magnetorotational instability, an effect which we have seen for protoplanetary disk in Philametric-Stokes last week, and which generally grows as soon as you have a gradient of angular velocity in your disk. And that can also lead to the growth of the magnetic field up to 10 to the 15, 10 to the 16 Gauss in the post-merger remnant. That is slightly easier to do in simulations than the Kelvin-Helmholtz instability, because the fastest growing mode at least is not at a smaller scale, but at a fixed wavelength that depends on the strength of the field. So if I have a 10 to the 12 Gauss field in a standard accretion disk from a neutron star merger remnant, it's going to grow on a length scale of about 30 meters. That is very hard for simulations to do still. The typical resolution in a simulation of a neutron star merger is more 200 meters than 30 meters. So that's a pretty big gap. If you consider that the cost of your simulations typically scales like the grid spacing to the 4th power. So it's a very big difference in cost. But if you artificially put a magnetic field of maybe 10 to the 14 Gauss, which is still 2 orders of magnitude below the eventual result of 10 to the 16, no, it's very easy to resolve in simulations. And the best simulations that have been done so far can actually get to 15 meters or so and actually resolve that even with somewhat realistic initial fields. So that's at least manageable. It's costly, but it's manageable. While the Kelvin-Helmholtz, there is less of a path forward to actually capture it in simulations. And that magnetorotational instability is what is going to drive angular momentum transfer in the remnant accretion disk. It gives you those viscous outflows of a long time scale. And it is also what is going to be probably the main source of heating in the remnant accretion disk. It is going to have to balance the neutrino emission to give you the evolution of the temperature in the disk. So this is an important effect to capture, certainly. Right. So if you include magnetic fields in your simulations, the kind of thing that you actually start to get, it's the main effect that is responsible for erasing differential rotation in the neutron star remnant through angular momentum transport. It is, as we have already discussed, the main driver of viscous spreading of the accretion disk, which is going to drive significant outflows over long time scales. And magnetic field, heating due to magnetic fields is going to be able to drive winds in the remnant accretion disk in the same way that I think you saw in some talks last week. And that is actually one of the main driver of the early post-merger outflows, so the ones on timescales of 100 milliseconds to a second. So the other half of the post-merger outflows, one half is the magnetically driven outflows, the other half is the viscous spreading over long timescales. So that you really need these effects if you want to properly capture the post-merger evolution and the outflows that come in mergers. But that's difficult to do in simulations because all those instabilities, all those things that actually determine what the outcome of the merger is in terms of magnetic field structure grow on very, very small length scales that are very hard to resolve in simulations. Any question? Yeah.
Do we see neutron stars with magnetic fields that large? Assuming you would be able to see remnants of previous.
We see magnetars, but probably not immediate. We don't think that they are the immediate aftermath of this necessarily. You could form a magnetar type field in a merger, but I don't think that we have seen a magnetar that is the immediate result of a neutron star merger at this point. But in theory, yes, you do see neutron stars with very, very large magnetic fields. And you do expect that the remnant of a neutron star merger will have a very large field. Yeah. Okay. So, the other important effect to capture that we have already seen in those outflows is the impact of neutrino matter interactions. So this is what is going to set the composition of the outflows. And the reason it is difficult to include in simulation is that it is a very high dimensional problem. What you would like to do is evolve the distribution function of neutrinos, so the function of time, position of the neutrinos, energy of the neutrinos, orientation of the momentum of the neutrinos. So it's a 6+1 dimensional problem that you need to solve for each type of neutrinos. And on top of that, there are very strong interaction with the matter, which that you have stiff source terms in your evolution equations, which require the use of implicit time stepping, and you have coupling between neutrinos of different energies, neutrinos of different species. It's a very demanding problem from a computational point of view, and so we only really can solve it for the moment with very approximate methods. And how approximate your treatment of neutrino is in your simulations has a strong impact on the predictions that you make for the composition of the outflows. So let me say, a few words on the current methods that are being used to give you an idea of how approximate it is. The most common, maybe the easiest to implement, is the leakage scheme. So in the leakage scheme, you look at one point, what is the temperature, density, composition of your fluid, and say, okay, what should be the emission rate of neutrinos, assuming that neutrinos can just free stream away from the current point. And then you look at the optical depth of your system, 2 neutrinos, from the current point to the boundary, to the main, and say, okay, how fast could neutrino diffuse through the entire system if they were limited by diffusion? And then you compare the two, and whichever one is the smallest is basically the limiting factor. Either you're limited by the diffusion rate or by the emission rate. And then you take that one as your actual loss of energy and change of composition due to neutrinos. It's a very rough estimate. It's only order of magnitude accurate because you cannot actually emit neutrinos in one place and reabsorb them in another place, which is what happens. Everything is determined locally. And your diffusion rate and emission rate are very approximate when you compute them in that way. And so it only gives you really a rough estimate of the cooling of the accretion disk due to neutrinos, but not a very good idea of what changes of composition, for example, are, because then you need to emit neutrinos, for example, in the neutron star, and recapture them in the winds. Another method which is used is to integrate over the direction of propagation of the neutrinos and integrate the evolution equations of neutrinos in the same manner. and then you can get evolution equations for example, the energy density and the flux density of neutrinos. That is what is called the moment schemes. That is the most advanced technique currently used in merger simulations. But it is limited by the fact that as in the equation of hydrodynamics, when you evolve the energy density and the momentum of a fluid, you need to close your system of equation with the pressure of the fluid. In the same way, in these moment schemes, you need to determine the pressure tensor of the neutrinos. But while in a fluid, you know that all the particles forming your fluid are roughly in equilibrium with each other. They interact a lot. In neutrinos, that's not the case. You cannot assume that they are in equilibrium. And so that pressure tensor is actually unknown, and you have to make some sort of approximation to figure out what that pressure tensor could be. You know what it is in optically thick region where everything is in equilibrium, but you don't know what it is far away when neutrinos are mostly free streaming. So that means that you have to make an approximate closure here for your system of equations, which is limiting you. There are other limitations which have to do with the fact that you don't know what the neutrino spectrum is, but neutrino matter interactions are very dependent on the energy spectrum of neutrinos. So again, you are getting errors of what we estimate currently is about a factor of 2 in the emission and absorption of neutrinos with this method. It's better than the leakage, but might still introduce significant errors in your predictions. And maybe the most blatant error that can happen when you use those approximate methods is the one shown here. Imagine that you send 2 beams of neutrinos from the bottom of your screen here towards each other. And these are neutrinos. They're not supposed to interact much. What happens if you use this analytical closure for the pressure of the tensor of the neutrinos is that the 2 neutrino beams collide and merge and form that weird interacting region. They are a single beam moving in the average direction of the neutrinos. The correct answer is the one on the right, where the neutrinos just cross each other without interacting. But you cannot do that with the approximate methods that we are currently using. One thing that we are currently developing and hoping to use is to use Monte Carlo radiation transport to give you the closure, and then that closure would be exact, and that's how you can generate the right plot. But it's a lot more expensive, and it's still in development. The current simulations have not used those methods yet. All right. So that's roughly where we are right now. We know that neutron star, and black hole neutron star mergers power both powerful electromagnetic and gravitational wave signals. And you can use those gravitational wave and electromagnetic signals to get information about the properties of the merging objects. And in the case of the electromagnetic signal, also to know, whether neutron star mergers are actually responsible for things like enriching the universe into heavy elements. And you will hear a lot more about the different types of electromagnetic signals, how we observe them in Samaya's talk, which will certainly talk about kilonova, maybe GRBs, and probably also radio emission. In terms of actually making numerical simulations of these systems and predictions for what the ejection of matter should be, for what the result of a merger should be, these are simulations that, as opposed to the black hole simulations that we saw a few lectures ago, involve a lot of additional physics that is difficult to capture in your simulation. So you have to take into account magnetic fields. You have to take into account neutrino matter interactions. You have, of course, hydrodynamics in the equation of state of neutron star, which is maybe not the hardest part to include in simulations, but has very important difficulties from the point of view of nuclear physics, of actually giving to people doing numerical simulations the correct equation of state. It's an important question as well. So all of that extra physics comes into play, and that makes the simulations a lot more expensive, a lot messier, and a lot harder to interpret. And currently, we have very good ability to do the pre-merger and the dynamical merger phase, but in the post-merger evolution, when the growth of magnetic instabilities become important, when neutrino matter interactions become important, our ability to reliably model these systems is still fairly limited. It's only really order of magnitude accurate. So we can predict, we can give trends, we can see what happens when a neutron star is bigger or smaller, we can see what happens when a black hole is more massive or less massive, but actually to predict the amount of mass ejected in a given merger and the composition of those outflows, which are both important for kilonovae, to do that from numerical simulation at this point is still a very approximate process that we are working on. And that's going to be important if we want to properly analyze upcoming observations of these neutron star mergers in follow-up to gravitational wave observations. And so that's probably where most of the work on the numerical simulation side will be in the next few years, is actually improving all that microphysics and trying to get closer to reliable models for the post-merger evolution of neutron star, and black hole neutron star systems. And hopefully at the same time, we'll get a lot more observations from LIGO of neutron star mergers as LIGO becomes more accurate to actually compare them to the result of these simulations. Thank you. I'll take any more questions that you might have on this.
How important is measuring the neutrino flux from these mergers for constraining these models? So I think you mentioned last week that neutrino flux, or there was no neutrino signal measured.
Yeah, so that I think that was discussed in Ariadna's talk. So the neutrino flux is too low to be observed for at the distances at which those neutron star mergers happen. In part because the flux is too low, in part because the neutrinos are actually relatively low energy, 10 MeV or so, which is not ideal. So yeah, you don't expect to be able to measure neutrinos unless you have a very, very, very close event. So it's not like a supernova where you can get some. In a supernova explosion, if you see the gravitational waves, you will definitely see a large neutrino flux. In a neutron star merger, the gravitational wave signal is much larger. You can see them much farther, but the neutrino flux, on the other hand, is not sufficient for you to measure it with current detectors. So yes, you don't get much constraint from the measured neutrino flux. We can predict it in simulations roughly, but you don't get constraints from actual observations. Where the neutrino flux comes into play is that it's important in setting the composition of the outflows. And so it's going to affect the kilonova signal, but indirectly, right? You're not going to actually measure the neutrinos.
What are the time scales for the evolution? Like, if you have two neutron stars colliding, if they don't form immediately a black hole, on which time scale they go through a supermassive neutron state and finally collapse into a...
That can vary a lot. You can pretty much find any time scale you want. It depends how close they are to the collapse threshold in part, and how much they have to redistribute angular momentum before the collapse. And the typical, the cooling time scales for neutrinos is tens of milliseconds. The angular momentum redistribution, it depends on the magnetic field growth, so it's hard to tell, but probably 10 milliseconds roughly. So that's going to be a first time scale in which something can certainly happen. If you need a longer cooling time scale or to lose some rotation, some angular momentum in the neutron star instead of just redistributing it, then it can be a much longer time scale. It's hard to tell. I think the ones that you can capture in simulations, which is the redistribution of angular momentum due to magnetic field or effective viscosity, if you want to model it that way, that takes from a few milliseconds to maybe 10, 20 milliseconds, but it's just that's the one that we can actually capture in simulations. That's one that can happen, but it could also be longer if it's a little bit farther away from the collapse threshold.
Can we get known equation of state inside nuclear star using observable data and numerical simulations?
So, for the equation of state, the constraints that have been, most of the constraints that have been obtained so far from the neutron star merger observation come from the gravitational wave signal and the tidal effects before merger. That's one way in which you can do it. Then less directly, you can use the electromagnetic signals, yes. For example, the current observations of the neutron star mergers tend to favor the idea that the neutron star did not immediately collapse to a black hole. Because if they immediately collapse to a black hole, there is very little matter which is ejected. And we do see a few percent of a solar mass of matter ejected. So most likely, the neutron star merger that we did observe did not rapidly collapse to a black hole. And if you accept that as a constraint, then that is a constraint on the equation of state of neutron stars. Eventually, I mean, yes, you should be able to go from here is the radius of a neutron star and the mass of a neutron star. Here is what electromagnetic signal you should see, compare it to what we actually see, and try to get some information. But the models are not good enough yet to be able to do that. And it's not just the numerical simulations. Beyond the numerical simulations, there's all the nuclear physics that goes into going from the properties of the ejecta to the actual kilonova light curve. There's a lot of uncertainties coming from the fact that we don't know the properties of all those neutron-rich elements that well. I mean, we don't observe them here. We have only rough analytical models that are extrapolated from more stable nuclei. And so actually knowing what the properties of a kilonova exactly is given the properties of the outflows is another difficult problem. And you need to solve both of those to be able to reliably extract information about them, about the merging objects. So currently it's at a very rough stage, right? We see some outflows, so it probably didn't collapse immediately to black holes, so that's a limit. But we should be able to do better once we get better simulations and better understanding of the nuclear physics. In theory, we can do better, but not yet.
Is there any observations or theoretical calculations or prediction for polarization of electromagnetic radiation? You didn't talk about polarization.
No, I didn't talk about it at all. In the kilonova, I don't know if anyone has looked into that. I'm not aware of any observations that have to do with polarization, but I'm not sure I would be if there was. So, and in simulations, we are definitely not there yet. The simulations don't actually even predict all of the electromagnetic signals are things that we don't do in simulations at all, because the gamma ray burst, the simulation of the merger itself cannot actually produce the engine self-consistently. So Omar talked a little bit about this last week, but if you want to model a gamma ray burst, you simulate an engine, but not something that is from the numerical simulations. You just assume, okay, what should the engine look like? How should it actually inject energy into the jet? And then you model just the jet and into surrounding matter. And then you can make some predictions for the electromagnetic signal. But the merger simulations with general relativity themselves cannot go to that stage. For the kilonova, again, we don't model the signal. We say there is 5 solar mass of material ejected, and then give that to people doing nuclear reactions and photon radiation transport through that material to get predictions for the electromagnetic signals. It's far removed from the engine itself, because we cannot follow that kind of long time scales, seconds time scale that are required for the R process.
There are such simulations for
so
no explorers.
Yeah.
They can elongate it, not spherically symmetric.
Yeah.
Result in some
So I assume that the jet simulations can get to something like that, but I'm not a specialist on that. The kilonova simulations usually are done in purely hydrodynamics with no magnetic fields, so it's going to be.
If there is a delayed collapse to black hole, would be expected to produce a comparable, somewhat comparable or in any way detectable gravitational wave signal?
So you do get some gravitational waves from the collapse to a black hole, yes. It is high frequency gravitational waves, and not with enough energy in that specific part to be reasonably detectable at the moment by LIGO. So the one that you might hope to expect is if you have a long enough ring down of the neutron star at a specific frequency that you might be able to observe. It's a few kilohertz. I don't remember the exact frequencies for the collapse signal. I remember seeing energy plots, and there is a significant amount of energy that goes into there, but it's at such high frequency, higher than the ring down, that you don't expect really LIGO to be sensitive to it at this point. But I mean, yeah, in theory there is a gravitational wave emitted, yes, and you can model it, but it doesn't seem very promising for observations.